recording. Thank you.
Okay, so we start, inshallah, our lecture for the 11th. And, yeah, this one. So what we will do today, inshallah, we have only one, maybe 10-15 minutes of new material. And I don't know if you checked your Blackboard. I posted the first worksheet. So this is done in groups of 4. So you have to divide yourselves, in groups of 4, and then you work together. It's supposed to be sort of discussion type of worksheet. There are something like 11 or 12 problems that you have to solve. It's basically on all what we've taken so far. So time permitting, at the end of the class, I will go over the solution, or at least hints of the solution, or hints to the solution of the problems, and then inshallah we'll carry it from there, because the quizzes and the exams are based on these worksheets. So please make sure you pay attention to them. Working in groups is very beneficial. When you work in groups, it helps you, just discuss the material, and then not only that, but also it gives you a chance to ask yourselves questions and so forth. It's very, very beneficial, and it has proven to be that way. So just so that we finish as I said, we finish the material for today, I'll just go to the last bit, which is dielectrics. Now, I'm going to ask you a question here. Last time we stopped at the parallel plate capacitor, and I think we got to the point where we discussed the fact that a parallel plate capacitor is a device that is used to, what is the function? It's an electronic device that is used to? Say again? Accelerate charges. Why does it accelerate charges? That's a very good answer. Why does it? Because? Yeah, because the electric, this is very important. I'm going to write this, I think I wrote it a number of times, and I will write it again. Once you have your parallel plate capacitor with setup, this is with charge Q, and this is with charge minus Q. And we said that you're away from the edges, so you're somewhere where the electric field is uniform. So uniform electric field. Then when the electric field is uniform, as we usually indicate that by drawing the lines parallel to each other and separated by the same distance. That's how we draw or indicate that the electric field is uniform. Now we said that when the electric field is uniform, then you can calculate the force, which is what? Does anybody remember? It's Q multiplied by E, right? Q is the charge. When you place a charge here, a small charge, Q, if you place it here, then it will be affected by the field. How does it get affected by the field? A force will be produced on it. Now that force, since the electric field is uniform, that force will be constant, right? And if you have a constant force, then what are you going to get? F is equal to ma. And it's the mass, this mass is the mass of that charge, mqa. So from here, you can calculate the acceleration, which would simply be F over mq, and therefore you describe the motion of, because if you get the acceleration, that's what you wanted to do. You wanted to get the acceleration so that you describe the motion of the object, or the motion of this charge. And that's what we're interested in. Okay? So please make sure that this is this sequence here. Now, E, we know how to calculate it, right? What was E equal to? E equal to what? Somebody, E inside the parallel plate capacitor, what was it equal to? Say again? Q? What was it? Q over epsilon naught A, right? That was the charge, the electric field inside. And as I said, we assume Q is constant. The surface area of the plate is constant, and obviously epsilon is the permittivity of free space, is also constant, so this will give you a constant electric field. Okay, and don't forget that the electric field is always directed from positive to negative. And not only that, we said that if you place a positive test charge, it will move along the direction of the field. And if you place a negative test charge, it will move against the direction of the electric field. And we said this is a property, or this is a characteristic of the electric field. In gravitational field, that's not the case. In gravitational field, everything goes down. Everything goes towards the center of the Earth. So that's the difference in it. All right, so this is where we, and the last thing that I talked about is just before the end of the class, is that we said that the parallel plate capacitor produces for us a uniform field. But in electronics, what it really is used for, it's used as a storing device, an energy storing device. So energy storing device. And how do we storing device? And how? Using something called the capacitance of a capacitor. Capacitance, if you remember from last time, what is it بالعربي ايش capacitance؟ السعة, right? And a capacitor بالعربي ايش؟ Capacitor, right? So C, if you remember last time, we defined C, the capacitance of a capacitor. What was it equal to? Anybody remember? Epsilon naught area over the distance. So what did I say about that? Remember the last thing that I said at the end of the last class? What did I say about the capacitance? We said it's a constant quantity, right? It's a constant quantity, and it depends only on the geometry, right? It depends on the geometry. A is the surface area, and D is the gap or the distance between the plates, and epsilon naught is what? Constant. What is it? What does it represent? It represents the permittivity. So also the space in between, the plates here matters also for the capacitance and for the electric field. Okay. So C here, it depends on the geometry. It's proportional to A, and it's inversely proportional to D. And also it's directly proportional to the permittivity of free space. What does that mean? That means if I somehow change the space in between the plates, what do? I change the capacitance. So let me write that down here just simply to. So let's say changing the space or the medium in between the plates will affect C, the capacitor. Okay? How? Because of this formula here. Right? We see that if we change this somehow. Now, how do we do this in electronics, in electronic engineering? The way we do that, by adding some material in between the plates called dielectric material. Okay, dielectric material. Does anybody know about these dielectric materials? Have you ever heard about these dielectric materials? What's so special about them? We'll talk about these. So anyway, so just so that because that's the next topic that we're going to talk about, is dielectrics. Dielectrics. Okay. So dielectrics. What do we mean by a dielectric material? It's an insulator that actually enables us to increase the capacitance of the capacitor. Increase the capacitance of the capacitor means what? Means that we will be able to store more energy. Got it? Because that's what we want. We want, energy storage device or energy storing device. So if I wanted to increase the amount of electric energy stored inside the capacitor, I need one way of doing it by inserting a dielectric material. Okay. Now let's see here. I have some very nice picture. I just want to show you how inserting a dielectric material will help us increase the capacitance of the capacitor. Now remember, I said this many times. This is in physics 2, in engineering courses. This is usually a very long chapter, part of a chapter. where we discuss these things, but in here we just wanted to see very quickly how this is done. So let's start with the top picture there. Okay. The picture at the very top. That's normal. That's something that we've seen before. We have a parallel plate capacitor, and the capacitor is Q or plus Q on this side, minus Q on the other plate, and then we have a nice uniform electric field in between them. Okay? Now, that's A. B, what happens if I insert a dielectric material? What do you mean by a dielectric material? It's an insulator that has dipoles in it. Dipoles, that means plus, negative, plus, negative, plus, negative, plus, negative. Now, originally, when I put them in, they are somehow oriented randomly. I can draw that here, oriented randomly, and when I put them in the electric field, somehow they become polarized. See the word? Polarized, meaning that they polarize, the poles are, aligned. Okay. So let's see. Now, initially before, this is my positive plate, negative plate, and this is my positive plate, and then I put this dielectric material in between. Right? My hope, the purpose of putting the dielectric material in between is to do what? To increase the capacitance, to increase C, which we put it somewhere. So these guys at the beginning, they're somewhere like this. They're somewhere randomly oriented, and as soon as I put them inside the capacitor, then they become polarized. That means negative, the positive will be attracted to the negative, and so forth, and the negative will be attracted to the positive. Okay, so that's something that automatically happens as soon as you put in the dielectric. Now the question is, what happens to the electric field inside? Now, if you remember, my electric field there is simply, uniform, nice lines going in. Now, but when I put the dielectric, some of the electric field lines, if you remember last time, some of the electric field lines will be terminated. Remember the electric field lines, the property of the electric field lines, they originate at the positive test charge, and they are terminated at the negative charge, right? That's always the case, right? So they start at the positive, and then they terminate it. So that's the property of the electric field lines. If you see here, whenever they see, so this one doesn't see anything, so it's terminated here. But this one here, it's terminated, starts here and terminated here. This one goes right through. This one terminated here. So that's what happened. Now, remember what I said last time about the electric field lines. Somebody, what does the electric field lines tell me? They are an indication of the strength of the electric field, because they are proportional to Q. If they are proportional to Q, therefore they are proportional to the electric field, the strength of the electric field. As you can see here, over there are a lot of them. In here, there is a few of them. What does that tell me about the electric field here? Does it go down or go up? Go down. So that means the first thing that you should write in your notes is that when you insert a dielectric material, the electric field is decreased. The electric field is decreased. Got it? When you insert a dielectric material in between the plates, remember, dielectric material is an insulator that is made up of these dipoles, right? Positive, negative. You know what the word die in English is, right? Right? Okay? So this, therefore, once I put the dielectric material, polarization will occur, and then we have a decrease in the electric field. Okay, the magnitude or the strength of the electric field. Did everybody write it down? Okay, so now we agreed that the first thing that, and this is again a multiple choice type of question, with the, where we ask you, in you insert a dielectric material in between the plates, what happens to, for example, the electric field? What happens to the electric field? Decreased. The question is, decreased by how much? The question is, by how much did it decrease? The electric field, let's call E0 is my initial electric field, right? Is decreased by, as you can see here, E is the new electric field, is decreased by this amount, right? So I multiply it by some factor. This kappa here is called the dielectric constant. Okay? This is the dielectric constant. So if the dielectric constant is a quantity, is a constant, that is greater than 1. It's unitless. It does not have any units, and it's always greater than 1. For air, the dielectric constant is equal to 1. Okay, for air, kappa is equal to 1. And then when you go to other materials, wood for example, plastic for example, grease for example, so forth, these values, they become greater than 1, 2, 3, 4, 1, 1.2, so forth. Okay, so the reduction of the electric field is by this factor here. Okay, so the first thing again, if I may repeat again, is that the electric field inside the parallel plate capacitor has decreased by this amount, by this factor, sorry, not by this, by this factor. It's 1 over kappa. All right, fine. Now the other thing that if you follow with me here, that the electric field is defined as Q over epsilon A. Okay, that's something that we defined here, right? And E is, remember, it's reduced by kappa. And C will be increased. Remember, we said that the reason for inserting this dielectric is to increase the capacitance. So putting the capacitance in, putting the dielectric in will make this C nu will be simply kappa multiplied by epsilon naught A divided by D, which is the C0, the initial capacity. Okay, that's it. That's all we need to know about capacitance and dielectric. Okay? So if I repeat again, and please I want help from you guys, the purpose for the reason for adding a dielectric material inside the capacitor is to increase its capacitance. Okay, now by the way, engineers, they use it for more than that, because one way, if you one more advantage is that when you insert a capacitor, it makes, it helps you make the plates parallel. So it also physically set the plates in place. But that's an additional, another additional advantage. But for our own purpose, inserting a dielectric material is simply increases the capacitance of a capacitor. Okay, that's it. That's all we need to do. So let me just see here. I think I have an example here. Let's look at the second example, second exercise here. Okay, a parallel plate capacitor has a capacitance of 7 microfarad. When filled with the dielectric, so this is C or C nu? C. Is this C0 or C nu? Because remember we have C0, right? We have C0, the initial one, which is simply what? Epsilon A divided by D. That's the initial capacitance. C nu, yeah, kappa multiplied by C0. So this is here, a parallel plate capacitor has a capacitance of when filled with a dielectric. That means it's C nu, right? It's C nu when filled with a dielectric. So this is this guy here. Okay. Now the area of each plate is 1.5 meters square. Okay, that's very long. It's supposed to be millimeter square. That's a huge plate. That's a mistake there. Okay, and the separation between the plates is 1.7. So this is millimeter, not meter. This is millimeter square. Okay, so let's just look at this. So I have C nu. It's simply kappa multiplied by epsilon A divided by D, right? Kappa is the one. What is the dielectric constant? He wants kappa, right? And he wants, of course, I can calculate from here. And C nu, he told me it's equal to 7. 7 times 10 to the, what's a micro? 7 times 10 to the power of minus 6. That's farad. I have to change that. And kappa is the one he wants. Epsilon, we said it's equal to 8.85 times 10 to the power of minus 12. The area square is now, we said it's 1.5 millimeter square, right? So it's 1 minus 3 and minus 3, it will be minus 6, right? Okay, that's the area. And the separation between them, D, is 1.0 times 10 to the power of minus 5 meters, and that's it. So the only thing that I don't have is what? Is this kappa right here. and then I can use my calculator to calculate that. All right? Okay? Any questions? Any questions? No questions? So this concludes our first module. Okay, the first module on. This is a question that in the worksheet. So the solution is here, but I'll comment on it when we get there, inshallah. Let me just. So what I'm going to do now, if there are no questions, I'm going to give you an overview, sort of a review of module number 1, and then after that we'll look at some of the questions on the worksheet, and okay, so this is a review. Now the good thing for you, now we have a videotape. So inshallah today after I go home, I download this and I upload it on YouTube. You all visited my channel, right?
Yes.
Okay, so it will be uploaded on YouTube, and then you can use it for to do your homework and review. All right. So what was the objective at the beginning? What was our objective? What was the objective in module number 1? What were we set to do? Yes.
Coulomb's law.
Say again.
Coulomb's
Well,
law.
Coulomb's law is one of the things that we took, but what was our objective? Our objective is, okay, what do we want to do with the electric field? We want to study the motion of a charge in a uniform electrostatic field. Okay, that's what we want to do. We want to look at the motion of charges in electrostatic field, because that's something that we did not do in physics 1. In physics 1, just I always wanted to refer to this because I wanted to make a comparison. In physics 1, you have the gravitational field, the Earth, right? Earth is here, and then you have capital G, let's call it capital G, the gravitational field, and then you have a force which is equal to what? mg. Any mass somewhere in the field will be what? Will be attracted towards the center of the Earth. And this will always be the case, right? That's right? So unless you hold it, it will always go down towards the center of the Earth, which is in our definition down, just downwards. Right? Now, when we go to electrostatics, the issue or the problem is a little bit different, right? Because remember, you start with the field, and any field will give you a force. And if the field is constant, the force is constant, then you get to uniform acceleration and you can describe the motion. Okay? So this was let's say the physics 1 case. In physics 2, when we talked about charges, we have a charge or a group of charges, Q1, Q2, Q3, Q whatever, and then this is I have an electrostatic field, E field. There are some let's say some differences between this scenario and this scenario, right? For one thing, in here, there is something called a zero, right? Do you remember that? There is a point in this vicinity here, or in this space, where the force can be 0. Remember we calculated that? This is not the case here. If you're in the field here in gravitational, if you are somewhere in the field, you're going to experience a force. But here, there is a some way you can set it in which you can get a 0 force. And 0 force means what?
No motion.
No motion. So it means that in the electrostatic field, unlike gravitational field, we can have points where the electric field can be 0. We can set it, we can select it. And we saw that. We saw that if you have a charge here Q, right, and another charge here Q, only that. Both positive. Somewhere in the middle, in between these two charges, the field will be equal to 0. So if you manage to place that charge there, then your force will be 0. Okay. So that's the concept, and this is all because in electrostatic field we have gravitation, or let's say attraction and repulsion. While in the gravitational field you only have attraction. only. Okay. So anyway, so that was the sort of the introduction, and then we looked at a number of things. First of all, we looked at the net force, F net, and we said F net will always be equal to F1 plus F2 plus so forth. And F1, the force due to charge 1, charge 1 due to charge 2, due to charge 3, due to charge 4, and so forth. So, and remember, the way we calculate this F1, F2, F3, using something called Coulomb's law, where, what does it say? It says, R12 squared. This is the magnitude. Let's just make sure that we're talking about the magnitude. And one thing about Coulomb's law is that it calculates it forces you to calculate the force in pairs. Meaning that if you have 3 charges, you have to calculate F due to 1, F due to 2 on 3. Okay, so you have to do it in pairs. That's the way Coulomb's law. And then you sum. So if I have, because we're recording this. So suppose that I have 3 charges. 1, 2, 3. Right, these are 3 charges. Forget about these guys. If I wanted to calculate the net force on 3, F on 3, the net force, then the way I have to do it, I have to calculate this force, which is F1 on 3, and then I have to calculate this force, which is F2 on 3, and then I add them vectorially. So as vectors, F net on 3 will be equal to F13 plus F23. Okay? That's called the superposition. Okay, so you take these in pairs and you add them up. Okay, that's the way Coulomb's law. So all right, we only looked at, because this is again, I think I mentioned this a number of times, this is simply a sort of introduction so that you understand the electric field and the electrostatic force and so forth. We only did it along the line. So we did if the force is here, the charge here, and then we looked at the force along this line only in one dimension only, because that's what we're interested in, and only 2 charges. So that was the force. And then after that, we looked at the electric field. Now, what was the definition of the electric field look like? Now remember here, please don't forget that the force depends on the magnitude, it's proportionally depends on the product of the magnitude of the charges, and it's inversely proportional to the distance, and it's directly proportional to this k, which k is equal to, what is k equal to? 1 over 4 pi epsilon naught, depends on the material or the vacuum or the medium in which these charges are located. Okay? So that's just so that and the other thing that you should pay attention to here, that the direction of the force, what did we say about the direction of the force? What was the direction? If I want to find the direction of this force here, this is charge 1, and this is charge 2, and I wanted to find the direction, this is F1 on 2, right? And I wanted to find its direction, where its direction will be along the line connecting the 2 charges. So this is the line connecting the 2 charges. And then I come in here, okay? If it is positive and this is positive, where will the direction be? This way. If this is positive and that's negative, the direction will be this way. So let's just take negative and positive, then it's this way. That's the direction of the force. But we say the direction of the force is always along the line connecting the 2 charges. Okay? The next thing that we talked about is the electric field. We said that the electric field, by definition, is equal to what? F divided by Q, where F is the electrostatic force and Q is what? Is a test charge. We said we imposed 2 conditions on this test charge. We said it has to be small and it has to be, or not, we selected it to be positive. So just for agreement, so that universal agreement, that we said this force, this charge, let's select it as positive, and we select it to be very small so that it does not affect the field. That means what? That means if I have these 2 charges, I wanted to come and calculate the electric field here at this point, then I have to calculate the force on some test charge here, and then divide by the test charge, and then I get the field. Okay, the electrostatic field. Okay? Is that clear? So force, field, and then the next thing we said, which we started the last class, we said we wanted to produce, or we wanted to do things in uniform electric field. So we talked about uniform electric field. Okay. Uniform electric field. And we said we can produce a uniform electric field using, how do we produce a uniform electric field? Yeah, one way, the best way, or the easiest way of producing a uniform electric field by using what's so-called the parallel plate capacitor. Okay, the electric field outside the parallel plate capacitor is equal to zero, right? And the inside the parallel plate capacitor is equal to constant, and that constant value is equal to this number. Is this determined by this number, right? And the electric field lines, as I said a few minutes ago, they are always directed from positive to negative. And since this is constant, that means it's going to, or uniform, this is going to give me a constant force, right? And since so E constant, that will produce for me uniform, sorry. Uniform. This will give me F constant, and if F is constant, that means A is uniform, the acceleration is uniform, which is same as constant, and then I can use my equations. V2 is equal to V1 plus AT, and delta X is equal to V0T plus a half AT squared, and V2 squared is equal to V1 squared plus 2A delta X. Okay? What do these equations do for me? What do they do for me? They describe the motion for us. Okay, they describe the motion for us. All we did from here, we found the acceleration. Once we found the acceleration, we can come in here and calculate the time, calculate the distance traveled, calculate the speed, calculate whatever. Okay. Now, one thing that we did last time in one of the examples, we noticed that if you place a charge such as electron, what's going to happen to it? If you place a charge such as electron, you place an electron here, right? So here, you place an electron here. What happens to it? Yeah, but what happens to it? It will, remember the magic word? It will accelerate, right? What does accelerate mean? What does accelerate mean? Its speed is constantly increasing. And we saw it's constantly increasing by a lot. Remember when we compared its acceleration to the acceleration of gravity, we saw that there is 17 zeros, while with the acceleration of gravity is 10. So the difference between the acceleration of this electron is huge, is very huge. That means once I release it, it will go very fast. If it goes very fast, that means its kinetic energy is going very, increasing very rapidly. That's very important, okay? And then last thing that we did, so let me just write these, because these are very important formula that you need to know. So E inside the parallel plate capacitor is equal to Q over epsilon A. Okay, and E is directed from positive to negative. Okay, and then that's the direction. So this is the magnitude, and that's the direction. And then F is equal to what? What is it equal to? Q, right? The Q of the multiplied by E, right? If Q is positive, then the direction, its direction is along the direction of the motion. If Q is negative, then its direction is, and which is not the same as what we had in gravitational. Because in gravity, everything goes down, right? And here, it depends on your sign, right? And once we did that, then we can find the acceleration is equal to F divided by m of Q. And once we find the acceleration, we can describe the motion using these what's so-called kinematics equations. right? And the last thing that we did, we described two things. We described the capacitance, C, which we said epsilon A over D, and then we said that the dielectric, adding a dielectric, will increase the capacitance and do what? Increase the capacitance and decrease the electric field. If you increase the capacitance, that means you increase the energy. Okay? Increase the energy stored in it. And that's it. That's all we have to do in module 1. If you understood these, 5-10 minutes, this is all we need to do. Because our objective from the beginning is to understand how does a charge or a group of charges, when they are close to each other, what happens? What is the force between them? What's the electric field produced? And if I place a charge in that electric field, what happens to it? How does it move? Okay? And how, meaning describing its motion. Okay? So let's look at, are there any questions before we go? So remember what I said at the very beginning. At any time when we finish a module just like today, you should expect a quiz. So your quiz will probably be on Monday or Wednesday of next week. Okay? So that's any time we finish a module, you immediately expect, first of all, we'll take the worksheet, the one we're going to start today, and then after that you should expect a quiz. And if you understand here, or at least you attended the lectures, and you do the homework, which is the group sheet together, you will not have any issue with the quiz. The quizzes are usually based on what we take in the class and what you do in the worksheet. Okay? Question?
We have two quizzes on Monday.
That's not my issue. We don't discuss these things. You're a university student. University students are expected to do whatever. Whatever we tell them, they do. That's what university is, right? Okay, we can't talk about that. Don't worry about it. The most important thing is understanding the material and doing the work. And then, having the quiz tomorrow. Today, that's all things that we can talk about. Okay, let me just show you where the worksheet is. Okay, so this is your blackboard. Where is your blackboard? Blackboard. And if we log in, okay, so if you go to course documents, this is the lectures, and this is, I added this morning, the group worksheets. Okay, so the first one, the worksheet has to be solved in groups of 4 students, and 2, it is due on Wednesday, October 5. Okay, so I'm giving you 1 week to do. Okay, you shouldn't need that long, but for the first time, let's just do it and see what we can. So let's just, I'm going to go over some of these things, some of these questions with you very quickly. Just give you hints here and there. If you want to take 1 or 2 minutes to, do you have your groups already? No? You should form your groups. So I'll give you 1 minute to form groups now. Quick. Yeah? Go sit beside each other, groups. Your group should come to you. Yalla, quickly, very quickly. Okay, you stay here because you're doing that. Okay?
One more.
Yalla, quickly, come on.
Aisha.
I'm just going to give you hints for each of the questions. So 4, who does not have a group? You don't have a group? Okay, so who does not have a group yet? Who has 3? Okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You can work with one of these guys. We're missing some students today. Yeah. I should start taking attendance. Let's actually take the attendance since there are some people missing. can you just take it 10 minutes just to one piece of paper? Name and student number. Put the date. Today is the 29, right? Yeah. So September 29. Okay, so let's look at these questions. All right. Remember what the exercise meant to at least to take place. So you're supposed to meet somewhere outside, maybe in the dorm, maybe in the cafeteria, maybe in the study rooms in the library, somewhere, and you're supposed to solve these together. Guys, you're supposed to solve these together. Now I will take one for each group, so one copy for each group. That means I'm going to get 1, 2, 3, 4, 5 copies only. I know, and I've seen this in the past, where 1 or 2 people do the work and the rest don't do it, or at least they're lazy. Always, it's always the case, and never always the case, the people who do the work are the good people, are the good students, are the high achievers. And the people who tag along, okay, do the homework, yes, you will get your mark, because remember the worksheet is worth, the worksheets for the group, is worth something like 7 marks. Yes, maybe you will get the 7 marks, but remember, the quizzes are based on this, and the exams are based on this, and sometimes I take the same problem, the same exercise from the homework and I put it there. I just change a few ideas here and there. Okay, so please be sure you take this serious. Okay, so the first question, find the electric field, E, at a point located in the middle between 2 point charges. Q1 is equal to this, and Q2 is equal to this. When the charges are separated by 3 millimeters. So I have one charge here, let's call it, that's Q1. Q1, it's positive. And Q2 here is negative. Okay, this is positive, this is negative. And he wants you to calculate the electric field somewhere in the middle point. So the electric field in the middle. So this is my 3. So the point is here, 1.5, 1.5. Remember how we calculate the electric field. We calculate the electric field by first calculating, if you want to do it the long way, calculating the force and then dividing by Q. Right. So if this is Q, this is Q, small q, that's short, Q naught. Then this times this divided by the distance multiplied by K, right? And this is positive and positive, so it will be, right? Yeah. This way. And this is negative and positive, it will be this way, right? So in this case, the force and the electric field are both directed along, well, this is my I hat, positive I hat, and this is my negative I hat, along negative I hat. Okay, so my electric field, E, will be simply K, right, Q1 divided by, let's call it E1, divided by R1 or 1.5, is it millimeter? Yeah, millimeter. So times 10 to the power minus 3 squared. That's my E1. And it is directed along minus I hat, right? And E2 will be again KQ2 divided by 1.5 times 10 to the power minus 3 squared minus I hat. Okay, remember how I did this? I simply did F over Q naught. That's what E is. E is equal to F over Q naught. F will be simply Q multiplied by Q naught. If I divide by Q naught, I get Q1. And this one, Q2 multiplied by Q naught. If I divide by Q naught, I get Q2. Right? And then you add them up. Okay? Because the sum or the net will be E1 plus E2 in the negative direction. Okay? That does. Is that clear? Questions? No? All right. So you have the hint. Given, are there no questions? You guys are supposed to ask questions. You're supposed to make noise. So, you know, that's what the exercise should have. Given a 1 farad parallel plate capacitor having a separation 1 millimeter, what is the area of the plate? Yeah?
Why is this 1.5?
Say again?
Why is this 1.5?
This one?
Yeah, from what is this
1.5 because the distance is 3. He said separated by 3 millimeters. I said it's in the middle between them. And the middle is 1.5. Right? Because it's millimeter. I have to multiply it by -3 so to convert it to meters. Okay? All right, so here C, if you remember from the beginning of the class, is equal to, right? A divided by D. Okay, sorry, epsilon. Right. C, he told me it's 1 farad. Okay, epsilon is known. The separation is D, and he wants the area. Yeah. That's it. Very simple. Okay? Now remember, this is 1 millimeter. You have to convert it also. Okay? Let's keep on going. So make sure you write these notes down. I know you're going to have them on the video, but if you have any questions, please. Okay, the next question or the next exercise, we have a parallel plate capacitor that has 7 microfarads when filled with a dielectric. The area is 15 centimeters square, 15, again millimeter square, okay? And the separation between them is equal to that. Yeah. What is the dielectric constant of it? We just did this, right, in the, now the only thing that I've added here, find the reduction in the electric field inside the parallel plate capacitor to this. Okay, how do you find the reduction in the electric field?
Find the original electric field and divide it by.
You don't need that. It's true. What you said is true. You said find the electric field, right? And the initial electric field, which is equal to, what is it, Q over epsilon A, right? And then you multiply a kappa. But remember what kappa is. What's kappa equal to? Over. That's it. Yeah. So the reduction is really, you don't need to do any calculation. I remember giving this question in one of the exams, and people start doing all these calculations just like your friend did, and in fact you do not need to do that, because that's what the definition of kappa is. All right? Because remember, E0, right? E0 is equal to E in more. Okay, let's move on. Let's keep on going. What's the next question? Charged particles, 3 charged particles. 3 charged particles lie on a straight line. So they all lie on a straight line. That's 1, that's 2, that's 3. Okay? Q1, Q2 have the same sign. The distance between them is 20 centimeters. Find where a third charge, so this is 2 charges. Right? Find where a third charge, Q3, can be placed so that the static force is equal to 0. Okay, we did this in class, right? Just the numbers are different. So you wanted to find out if this is x, this will be, right? Because the distance is equal, 20 minus 6. Okay, and then you can work that out. Okay? That's it. Okay, what else? Question number 5. Question number 5 says that two protons are separated by that distance. What is the magnitude of the electrostatic force between them? 2 protons, electrostatic force. F is equal to K, Q1, Q2 divided by R12 squared. Magnitude. Okay. What's the charge Q1? What's the charge Q2? Protons. It's both positive. 1.6 times 10 to the power minus 19, and the distance is given. So it's a very straightforward question. All right. What else? Okay. This is in. The solution is in the PowerPoint. So all he wants you to find the ratio of the electrostatic force in comparison to the gravitational force between an electron and a proton. Okay, so in the hydrogen atom, you have the proton in the center and the electron is orbiting it. Okay, so the force between them. What do you expect the relationship between, or the comparison between the electrostatic force and the gravitational force? What do you expect the comparison? Is it bigger, smaller, the same? What is it? The gravitational force, thank you. The gravitational force versus the electrostatic force. What do you expect? So I have a proton here and an electron here, right? What do you expect the relationship between, or the comparison between, if gravitational versus if electrostatic? What do you expect? Which one do you expect it to be bigger? Yeah. Why? Somebody tell me. Yeah, because we talked about that, right? We talked about that. The gravitational force depends largely on the mass, and the mass is very tiny for these guys, so the force will be negligible. Okay, another question here, which this is taken from one of the old exams. So now I have two charges, Q1 minus Q. So this is positive and this is negative, located 2 meters apart as a point along the. So at some point here, along the the perpendicular and the middle. So this is same distance and it's perpendicular to it. It wants you to find which vector represents the direction of the electric field. Which vector of these vectors, 1, 2, or 3, represent the net electric field? The one in the middle?
Yes.
This one here? How did you find that out? How do you find the electric field? How do you find the direction of the electric field? You place what? A positive Q naught here. Right. This is positive. Where will the electric field be? This way, right? And this is positive, negative. The electric field will be this way, right? If I resolve this one here, let's call this is E positive, and this is E negative. If I resolve this here, I'm going to get a vector here and a vector here, right? And if I resolve this, I get a vector here and a vector here. These guys will cancel, and that's my vector. Did you see how I did it?
Yes.
Yeah? Because the way you calculate, how do you calculate the electric field? You calculate the electric field by placing a positive test charge on the point that you want to calculate the electric field. And that's what I did. I placed a positive test charge, positive, negative, it will be attracted. Positive, positive will be repelled. So these two vectors, when I resolve them, this one has a positive y component and a negative x component. This one has a negative component, y component, and negative x component. These two guys are the same because the distance is the same, so they cancel. And then I give these two add up. That's you. It's a multiple choice question in one of the old exams. Okay, let's question number 8. An electron that has that charge moves in a path perpendicular to the direction of uniform electric field of strength is. So I have an electric field that is maybe this way, okay? And I have an electron that moves perpendicular to it. So moves perpendicular to it, that it's moving this way. That's my electron, okay? How much work is done on the electron to move at 15 centimeters? We didn't do that. We didn't do the work. Okay, so stick this out. Okay? All right. Well, just, do you guys remember from Physics 1 what the solution is? Because the solution is just a snap. It's moving perpendicular. Right? What will the force be? What will be the angle between them? If the angle is 90, what will the work be? Because cosine 90 is 0. So it's not much here, but it's just because we did not talk about it, It's right here. FD cosine theta, the angle theta between them is 90, so the work is 0. Oops. Question number 9. Okay, a pair of parallel plate capacitors are connected to a battery while the capacitor is connected. The voltage pulled away. What is the ratio of the final energy stored to the original energy stored? This is the one that I want you to research. Okay, because I only talked about the energy, the capacitor as a energy storing device. Okay, so now I want you to just compare because what I have done here, I doubled the original distance. Okay, now you have to go to the capacitance, what happened to it if you double the original distance, and then look at the energy, what is it equal to in terms of the capacitance. Okay, not the electric field, the energy, U. So U, what is it equal to in terms of C and Q? Okay, so what is it equal to in terms of C and Q? And then see what happens to when you double the distance. What happens to C when you double the distance? C becomes half, right? When D goes to 2, so C is equal to epsilon A over 2D, right? If you take that out, we epsilon A over D half. So C would be a half, okay? That, and then you compare, plug it into the energy, and you get the result. Okay, the last one is something that, again, it's not challenging, it's just what we did before, where you have an electron moving inside the parallel plate capacitor, and he asks you all sorts of questions. Okay? All right, so if you can just start with them, yeah. It's...